All right, in this video, we're going to do the Unit 10B review, and hopefully after this review, you start to see some patterns and seeing how the kind of all goes together. So let's just get right into it. It says, determine the number of terms to approximate the sum of this series with an error that is less than 0.0001. And I need to get this ready to write on. So there's two types of error bounds that we've talked about. One of them was called the Lagrange error bound, and the other one was called the alternating series error bound. The Lagrange error bound is used when you're using a Taylor polynomial of nth degree, and you know that the error would be within that absolute value of the maximum next derivative of on some interval. We'll get to some of those in a second. But this is not talking about a Taylor polynomial approximation. This is using the terms of an alternating series. And the alternating series error bound is written something like this. It has the absolute value of s minus s sub n. Now, s was the exact value of this alternating series. Now this, I don't know if I did a good job at making sure we explain this, but the alternating series has to converge. And if I look at this, it's a p series. If I take away the alternating part, this is just a series 1 over n to the fourth. It's a p series where the p number is greater than 1. So it converges. I don't know what it converges to. If I knew what it converged to, I wouldn't need an alternating series error bound. I wouldn't need an error bound. I would know the exact number. So the exact value of this alternating series adds up to s, but I don't know what this is. And this is the approximation using n terms. That is equal to what we call the error, or the remainder, using n terms. And this is going to be less than or equal to the next term of the sequence. So this is a series using terms of a series, adding up the terms of a sequence to make it a partial sum. That will always be less than or equal to the next term of the sequence. So I need this to be less than 1, and then what is that? 10,000? 1/1000. So this would be what, a tenth, and then 100th, and 1,000th, and a 10,000th. All right, so this is what we're gonna set up. So now I gotta think, this is the part that I really care about. I'm gonna solve for n that way. So now I gotta think, okay, this is the absolute value. This is the absolute value of the next term of the sequence. So the alternating component in that series goes away, and I just have 1 over, but it's n plus 1 to the power of 4. Because that's what this would be, right? So that's less than, I'm gonna find out what makes that less than 1/10,000th. So here, just algebra, multiply both sides by the denominators. I get 10,000 has to be less than n plus 1 to the power of 4. Take the fourth root of both sides, and I get, what's that, 10? Less than n plus 1, subtract 1. It says n has to be greater than 9. So if I used 9 terms, I can't guarantee the error would be less than that number. So I need to use 10 terms. N is the counting numbers. It's like 1, 2, 3, 4, 5, 6. I need 10 terms. So the answer would be 10. All right, number 2, values for the function f and its first 3 derivatives at x equals 5 are given in this table below. What is the third degree Taylor polynomial for f around x equals 5? All right, so I'm gonna write this out. I'm gonna say p sub 3 for Taylor polynomial. Some people write it t sub 3 as x like that. I'm t for Taylor, I think p for polynomial. But I mean, it doesn't really matter. So p sub 3 of x would be equal to the function value at 5 plus the derivative value at 5 times x minus 5 plus the second derivative of 5 times x minus 5 squared over 2 factorial, or just 2, plus the third derivative of f at 5 times x minus 5 cubed over 3 factorial. we have to memorize this pattern. That'll help us get questions like this on the test correct. All right, so f of 5 is 2. So I'm going to replace f of 5 with 2. And then f prime of 5 is -1. Replace that with -1. F double prime of 5 is 8. So replace this with 8. And f triple prime of 5 is 18. Now I gotta pick which one is the same, so I'm gonna do a little reducing. You can probably already tell which one's gonna be. X minus 5. So based on this, A is not right. And then the 8 and 2 reduced to 4. So D is not right. And then the 18 over 3 factorial. 3 times 2 is 6. So 18 divided by 6 would just be 3. So this would be plus 3 x minus 5 cubed. So the answer is B. All right. Next one. Let f be the function defined by 3x cosine of x. On your paper, it might say 3x cosine. That's wrong. I didn't check when I printed these off, but for some reason when I print off a Google Drive, it doubles up the cosines. So it's just 3x times cosine x. What's the coefficient of x to the power of 5 in the Taylor series for f about x equals 0? So when they give you this, there's two ways to do this. We could list it out. I could say, just like we did on the last one, p sub 5 of x is equal to, and that's a f of 0 plus f prime of 0 times x. Don't write this down, by the way. X squared over 2, and I've got to go on, I got to do this for a while, right? All the way to the 5th derivative. And instead of that, I was put in this parentheses, put the 5 in parentheses, it tells you 5th derivative of 0 times x to the power of 5 over 5 factorial. Okay, the tricky part about this one would be, I've got to find the 5th derivative of the function. And the function has a product rule, and then a product rule, and there's gonna be all these product rules, and it's gonna be ridiculous. So, since this is Maclaurin, I know that cosine of x, the Maclaurin series for cosine of x, so cosine, the c looks like an e to me, so I think it's all the odd exponents, or the even exponents. So 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. And this goes on forever. But I want to know the coefficient of the 5th degree. And I'm like, okay, that's kind of scary, but I still have to multiply this by 3x. So f of x is equal to cosine of x, which is what we got, times 3x. So 3x times cosine of x, which just means multiply all these terms by 3x, and I would distribute it. So 3x times x would be 3x. Erase all this extra stuff. It's bugging me. And then 3x times negative x squared would be negative 3x squared, cubed, over 2 factorial, which is just 2, plus 3x to the 5th over 4 factorial. I want to know the coefficient of the x to the power of 5. So it's this right here. So it's 3 over 4 factorial, which is 3 over 4 times 3 times 2 times 1. 3's cancel, and I just get, this is 1 over 8. Final answer. The coefficient for x to the power of 5 of 3x cosine of x would be 1/8. Okay, something else I want you to notice. George, this is for you. You asked this question the other day. I don't even know if you're going to watch this video. But this is a polynomial. It doesn't look anything like cosine of x. So if I wanted to rewrite like cosine of x, it would be this series, -1 to the power of n. It alternates, and it's even exponents. That looks nothing like cosine, because it's a polynomial that's used to approximate. But if I have an infinite number of them, if this series goes on forever, it becomes exactly equal to cosine. So taking the derivative of this is not going to be like, it can't look at it and just kind of know what it's going to, I don't know what I'm saying. All right, anyways, number 4. Find the third degree Taylor polynomial for the function f of x is equal to square root of x around x equals 2. All right, so this one just got to build it out. I'll say p sub 3 of x is going to be equal to it's around 2, so f of 2. It's not Maclaurin, it's not on a plug in 0. F prime of 2, x minus 2 over 1, plus f double prime of 2 times x minus 2 squared over 2, third degree, so one more. Third derivative of 2 times x minus 2 cubed over 3 factorial. So I gotta go to the side and say, okay, f of x is equal to x to the 1/2. I'll write it as x to the 1/2 because I'll do, the derivative will be a power rule, it's be easier. So 1/2 x to the negative 1/2. Then f prime would be, negative 1/4 x to the negative 3 over 2. Triple prime of x would be positive 3 over 8 x to the negative 5 over 2. Plug in values of 2. F of 2 would be square root 2. F prime of 2 would be 1 over 2 square root 2. Double prime of 2, what's that? Negative 1 over 4 square root of 2 cubed, and 2 cubed is 8. And then third derivative at 2 would be 3 over 8 square root of 2 to the 5th. 2 to the 5th. I could rewrite 2 to the 5th as what? What's 2 to the 5th? 2 times 2 is 4. 8, 16, 32. And I can just rewrite that if I wanted to. I don't know I'm rewriting this. It doesn't really matter. It would be 16. So 4. 4 times 8 is 32 with the 2 left over. All right, so all of these numbers are going to be plugged in to my general Taylor polynomial. All right, so it'd be p sub 3 of x is equal to square root 2. And then f prime, it would be f prime of 2, so this plugged in right here. So what is that? Plus x minus 2 over 2 root 2. And then it'd be negative x minus 2 squared over, I guess I could reduce this, 4 times 2, so 2, 8. Wait. So this would be what? Negative 1, 4 times 2, 2, 8 square root 2. And then, but it's times 2 already on the bottom, so it'd be 16. And then the last one would be plus x minus 2 cubed over 3 factorial would be 6. 6 times 32, but I guess the 3 and this 3 would cancel, but there'd be a 2 left over, so 64 square root 2. All right, final answer, all reduced. All right, what is the coefficient of x cubed in the Maclaurin series for the function 1 over 1 minus x squared? All right, so the Maclaurin series for 1 over 1 plus x is equal to 1 minus x plus x squared minus x cubed plus ... right? The general form is, I think it's alternating, just x to the n. And if x is in between, or the absolute value of x is in between 1 and negative 1, okay, so if the x number, that's basically your r number in the geometric series, if that r number, we call it x, if that's in between, if the absolute value of that number is less than 1, then it converges. Just for fun. I don't know why I told you that. Okay, 1 over 1 minus x So I'm trying to make it look more like this, 1 over 1 minus x. So I need to make it plus a negative x. Then that would be equal to 1 over 1 minus x, right? So to do that, plug in negative x for all the x's. So this would be equal to 1. Okay, it's minus, but a minus x would be plus x. Negative x squared would be plus x squared. Okay, it's negative x cubed times another negative, so plus x to the power of 3. And I think you'll see the pattern, right? It's just plus, 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 and it goes up by one exponent. Now, if I want to find 1 over 1 minus x squared, that's going to be 1 plus x squared plus x cubed plus dot, dot, dot times itself. And you think, I don't want to multiply these forever. I don't need to multiply this forever. I'm only trying to find the coefficient of x to the power of 3. So if I did first, and if I distribute all of this through, the first time I get 1 plus x squared plus x cubed, and then plus more stuff I don't care about. Then I do x times 1, so plus x squared plus x cubed. So I multiply this all the way through, do 3 of those things. I only care about the x cubed. X squared times x, so plus dot, 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 plus x cubed, and then the x cubed times 1, it'd be dot, 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 all the stuff I don't care about, x cubed. And when I combine like terms, I see that there are 4 x cubed terms created. So this would be something 4x cubed. Something, don't care. All this something, don't care. Don't care. All I care about is that the coefficient on x cubed is 4. All right, Lagrange error bound. So as soon as I see this little max of this, what this is saying is the absolute biggest value of the fifth derivative of f on the interval from 0 to 2 is 3.6. The absolute biggest value in absolute value of the sixth derivative of x between 0 and 2 is 8.1, and similarly that. Okay, as soon as I see that, I'm thinking Lagrange error bound, and they even tell me Lagrange error bound. So let P be the fifth degree Taylor polynomial for a function f around x equals 0. Information about the maximum, the absolute value of the selected derivatives of f over the interval 0 to 2 is given. What is the smallest value of k for which the Lagrange error bound guarantees that? Okay, the Lagrange error bound is, so let's see. So you have this polynomial and it's centered around 0. So there's this actual function value, I don't know what it is, that it might look like that. What the Taylor polynomial is doing is it's approximating, this one's using 5 terms, and it might, 5 degrees, and it might look like this. What we're trying to figure out is, okay, this is at 0. At point 2, how far off is our approximation? It might not be very far off at all. The further I get away from my center, the bigger the error has the potential to be. So the Lagrange error bound gives you a range on how far off it could be. And it's going to be a conservative estimate, so it's going to take into like worst case scenario, how much could it be off by? So Lagrange error bound says the exact value of the function at point 2. Now, point 2, this is good. Point 2 is within this interval that they give us, right? So they gave us the error bound for these derivatives all the way from 0 all the way to 2. Now, we are centered around 0, and we're approximating at point 2. So point 2 is pretty close to 0. But we're going to use the error bound all the way to 2, so it'll be over the top. Okay, a lot of the times, they give you the error for that interval where it would be exactly like where you're approximating and where it's centered. So usually this interval is like 0 to 0.2. But this one just happens to be a little bit bigger, but we're not going to worry about that. If it's, as long as 0.2 is within that interval, Lagrange error bound says it's going to be good enough. Okay, this is the exact minus the approximation. Okay, I don't know what n is, right? Maybe I should. There should be a little 5 there. Let p be the fifth degree Taylor polynomial. I'm going to put a 5 here. That tells me the Lagrange error bound says this is equal to the error. I should have put a 5. Of, what would it be, 0.2? So x is 0.2, c is going to be 0. This is less than or equal to the absolute biggest value of the next derivative. So since our n number is 5, the next derivative would be the sixth derivative. I put that in parentheses, so it doesn't look like it's the f to the power of 6 of z, and I'm going to specify z is within 0 to 0.2. Okay, our maximum values they gave us are even bigger than that, so we're going to be good. The biggest value from 0 to 2 is 8.1, so the biggest value, if I want to say the absolute biggest from 0 to 0.2, it might be 8.1. I wish this would have been a 3, so you can kind of tell it doesn't have to be like, it's not a mistake. When you write out Lagrange error bound and you write z here, just specify that 0 is in between your center and the number you're approximating. That would be x minus c, so 0.2 minus 0 to the power of 6 all over 6 factorial. The absolute value didn't need that big. Z is in between 0.2 and 0. I've got to show that that is... I'm trying to find the k. So I'm trying to find out what is the absolute, or the worst case scenario. All right, so the maximum value of the sixth derivative at z would be 8.1. I got that from the information they gave me. So this is 8.1. I'm going to take away the absolute values because they're not needed now. 0.2 to the 6th power over 6 factorial. And that's a safe stop. I went ahead and placed it to my calculator. This was equal to 0.000000. So 6 zeros, 7, 2. So what this is saying, the Lagrange error bound says if I used a fifth degree Taylor polynomial, so I built that out, that polynomial out, like we've been doing, and I plugged in 0.2, that number that gave me would be off by no more than this for the exact value, which is pretty cool. All right, let's see how many, probably get like maybe this page done before class starts. Okay, I don't know. Find the interval of convergence for the power series. Okay, interval of convergence, I use the ratio test. So I'm looking at this and I know the center is 3. The center comes from the x value that makes this all like 0 out. If I plug in 0 for x, that's going to be a series of 0 plus 0 plus 0 plus 0. Of course it converges. It's just 0 added up, so it adds up to 0. So I'm going to do the limit as n goes to infinity of the n plus 1 term. So plug, and it's going to be absolute value. The ratio test is absolute value, so the alternating part is not needed. Don't write it. Excuse me. It'd be x minus 3 to the n plus 1 divided by n plus 1 times 3 to the n plus 1. And I'm going to divide by the n term or multiply by the reciprocal. And I'm going to go ahead and skip straight to that step. I think we've done that enough by now. We're good. Okay, at this next point, I need to carry over my limit statement. So the limit as n goes to infinity. And I'm going to rewrite this as x minus 3 times x minus 3 times n. I will rewrite 3 to the n, so I'm going to keep the n plus 1. Write it as 3 times 3 to the n. Just copy everything else down. We're going to look at which n terms, or which terms cancel out. So at infinity, basically these factors just cancel each other out. So we're trying to find the limit. So this cancels, that cancels, And I'm left with the limit as n goes to infinity of x minus 3 times n over 3 times n plus 1. So this limit as n goes to infinity, the limit as n goes to infinity, this is basically 1. Because I've got a huge number over a huge number plus 1. That limit is basically, that's just a factor just 1. Those factors cancel each other out. So this would be equal to the absolute value of x minus 3 over 3. So this is a true statement because the limit of the n part would be like just times 1. So the ratio test is figuring out if the limit of the next term over the one before it, if that had given me infinity, then this this power series would only converge for the center. Because what it's saying is the next term divided by the one before it is growing up so huge, like the next term is just, it's unbounded. So the limit's not 0, of course it's diverging. It would only converge if I plug in 3 for x and it just zeroes everything out. Now if I found the limit and I found this was, instead of all this, it was equal to 0, that means it converges for all values of x. It doesn't matter what x is, the other terms are so powerful, it'll converge no matter what. But when I have this statement, I'm trying to basically figure out, okay, all the n's cancel each other out. We want to find out what makes this geometric. So I'm gonna start a new statement. I'm gonna say x minus 3 over 3. I want to find out what values of x make that less than 1 in absolute value. That's the geometric series test, basically. If the R number is less than 1 in absolute value, it converges. So to get rid of the absolute value bars, I put this in between 1 and negative 1, multiply everything by 3, and then add 3, and I get this. If it just, so the center is 3. 3 is right in the middle between 0 and 6. If it just asks for the radius, I would find the distance between 0 and 6 is 3, divide that by 2. Sorry, the distance between 0 and 6 is 6, divided by 2 is 3. So the radius is 3. I'll go ahead and say it. If it only asks for the radius, we would be done. But it wants to know the interval. So it wants to know if I plugged in 0, would it converge? And if it does, I'd underline to signify that 0 is included in the interval of convergence. I need to plug in 6 to see if it makes it work. And to see if it makes it work, I plug it back into the original series for x. So I should have said in the beginning of this question, right, Small? Because we're not done. So I've got to plug in 0 for the x. So I've got this series, negative 1 to the n plus 1, 0 minus 3 to the power of n, over n times 3 to the power of n. Now I'm going to rewrite this and mess around with it. Okay, this becomes another negative 1 to the power of n. Oh, I don't like this. All right, negative 1 to the power of n times a negative 1 to the power of n plus 1. If I was combining these, this would be negative 1 to the, what is that? That'd be, what's n plus 1 plus n? That's 2n, right? 2n plus 1 over n. So now I've got this series where the exponent is always odd. Negative 1 to an odd exponent is always negative, right? So if this was an alternating harmonic, it would converge. But is this an alternating harmonic? No, it's just a harmonic where all the terms are negative. So harmonic series diverge. So I would not include 0 in my interval of convergence. Now I gotta plug in 6. 6 minus 3 would be 3 to the power of n. That cancels. And I have an alternating harmonic. Alternating harmonics converge. You don't have to show all the work on these. If it asks for this on the FRQ, you would not need to like be super detailed. Just stating whether it's an alternating harmonic that converges, or it's a harmonic that diverges, or it's a general harmonic. Anything in this form, well, those are all positive numbers. That's a general harmonic and it diverges. But as soon as I make it alternate, it would converge. So usually when you plug in those endpoints, they're geometric series or they're P series. They're kind of easy to see. All right, so since I plugged in 6 and it worked, I need to include 6 in my interval of convergence. And for good measure, we said the radius is 3. All right, I'm gonna pause the video there and then do some more later. Thanks for watching. Hopefully this helped. Bye.